We're going to get back to that part I skipped, all those other pages. We'll get back to it later on. I wanted to go here today, so that it made a little more sense. We're going to talk about two things: compound events and the idea of what's called a probability tree. Probability tree diagram. Now, a compound event, you can see the definition here in your vocabulary box. A compound event consists of two or more simple events. For example, that one that we did on the worksheet a few seconds ago where they had all those tiles. Remember that one? If you just choose once, that's a simple event. But if you choose once and then you choose again, that's a compound event because it consists of two or more simple events. And as you saw, sometimes they can be dependent, sometimes they can be independent, depending on whether or not one outcome affects the other. Yeah.
If a question like comes up on the internet text about probability, and it doesn't specifically say that it's replaced, we assume that it's not replaced? Or
it will always specify one or the other, yeah. So, like tossing a coin twice, that's a compound event. We're going to get into this multiplication rule now. The probability of A and B occurring would be the multiplication or the product of the two individual events. So take a look down here at example 1. Right next to example 1, flipping a coin 3 times. That would be a compound event. This diagram is what's called a probability tree diagram, and I want to make sure you guys understand why this is so useful. If we didn't have this diagram, if I asked you to tell me what all the different outcomes were, if I had tossed a coin 3 times, what are all the different outcomes? Well, you have to try to keep it all straight in your mind. Well, there's tails, 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 or there could be tails, tails, heads, or there could be tails, heads, tails. That would be kind of hard to keep track of all in your mind, wouldn't it? You guys agree? A tree diagram can help simplify the process. Each branch off represents different outcomes for the event. The first toss, aren't there 2 different outcomes? But then from those 2 different outcomes, there's 2 more outcomes that could occur. That's the second toss. And then on the third toss, each one of those has 2 more outcomes. So if you toss a coin 3 different times, how many total outcomes are there? And what are they? Well, you can just follow the branches of this tree diagram. You can start here and go head, and then heads, and then heads. So there's 1 different result. Or there's heads, and then you can go down here and do tails. It helps you keep track not only in how many results there are, but what they are. So we're going to be practicing making these tree diagrams and then using them to figure out different probabilities. Okay? For example, let's ask a couple of questions down where you have this blank box here. Okay, question 1. What's the probability of getting at least 2 tails? Well, first of all, how many outcomes are there total? There's 8. So we know it's going to be out of 8 because there's 8 different ways that you could flip the coin 3 different times. There's 8 different outcomes. Now, of those 8 outcomes, how many of them have that? Now, what does at least mean? 2 or more. So there could be 3 tails would be a possibility. So take a look at your possible outcomes. How many of them have at least 2 tails? There's this one here. Let me circle. There's this one. There's that one. There's that one, and there's that one. So of the 8, 4 out of 8. So a tree diagram can really, and that was just using the tree diagram. We didn't have to use any fancy formulas. Even with using formulas, the tree diagram could make it easier. Go to the next page. Flip the page. Actually, we're skipping that example.
We're skipping everything in this pack.
We're skipping that. Go to the other page.
Yeah, you always allow
Here we go. Go to example 3 on that page. These are exactly like the problems that I had you do on the worksheet where you were choosing tiles with those letters on. There are 7 dimes and 9 pennies. Suppose 2 coins are chosen at random, and I want you to box this in without replacing the first one. These would be called dependent events because the outcome of the first has affected the outcome of the second because there's less coins. The probability of picking a penny and then a dime. That's what I'm asking you to find. Find the probability of picking a penny and then you pick a dime. This is just like the ones we practiced with those tiles. Find the probability of a penny and then a dime. It's equal to the probability of a penny multiplied by the probability of choosing a dime. This little line right here, I want you to write underneath, if you can, real small where it says this line. That means a given. Find the probability of choosing a dime given that the first coin was a penny. That's what was supposed to happen. If you choose a penny, what's the chance that you then choose a dime? So, what's the chance to choose a penny?
16 out of 9. 9 out of 16.
There's 9 pennies out of the 16 coins.
And then picking
But
a
now you've chosen a penny.
Your probability would be 7 out of 15 to get a dime.
So how many dimes are there?
7.
7 out of...
15.
You don't replace. This one's without replacement. So it's out of 15.
So how would you rank the first one with the penny? Or
9 times 7 is 63. Uh-oh. Oh boy, 15 times 16. That's 225, thank you. Now that may or may not, matter of fact, this does simplify. 63 out of 225, you're going to have to simplify it either on your fraction or on your calculator or on your own. 63 divided by 225.
It's 240.
15 times 16 is... You guys are lying to me. Well, now wait a minute. 220. Let's see. 63 divided by 2. Yeah, that simplifies as well. 63 divided by 240. If we simplify that fraction, is 21/80ths.
How did you do that again?
On the calculator,
Yeah.
type in the fraction. So 63 divided by 240, and then hit math. And then enter. I want you to put a line down here, split this. I want you to do one more probability. Find the probability of a dime and then a dime. What's the probability of choosing a dime and then another dime? Again, this is without replacement. Replacement does not occur.
So it would be 7 out of 16 and 7 out of 15.
Six
No, it's not.
out of 15.
6 out of 15, sorry.
Right? Isn't that right? Isn't that right? That's right, right?
Yeah.
What's right? What's that? What's the answer? No, that's the answer to this one. That's not the answer to this one. So, what's the chance that you choose a dime on the first pick? 7 out of 16. But if you don't replace the dime, it'd be 6 out of 15, which is 42 out of 240. That simplifies because they're both even. So 42 out of 240 is 7/40.
We have to put it to it.
I'd rather you leave it as a fraction. Basket, let's do this example 4. A basket contains 4 plums, 6 peaches, and 5 oranges. Where the heck are the vegetables? You should add, there's 5 carrots in there too. No, I don't know. What is the probability of picking 2 oranges, then a peach, if 3 pieces of fruit are selected at random? Now, we have to assume this is no replacement. They're just reaching and grabbing 3 pieces of fruit. So there's no replacement here. So we're multiplying each of these separate probabilities because this is an and probability, an orange, and then a peach. Or is it a peach? What is it?
An orange, then an orange.
And then a peach. Yeah, so it's an orange, and then an orange, and then a peach. All of those and means we're going to multiply. Or means plus, and means multiply. So orange,
1, 5.
there's 5 oranges to begin with, and then there's how many? 15, so it's 5 out of 15. But then if you've already chosen an orange, what's the chance you choose another one? 4 out of 14. Six out of 13. Ooh, these numbers are getting big. All right, 5 times 4 is 20. 20 times 6. 20 times 6 is 120. And then, oh man, 15 times 14 times 13. That's a calculator problem right there. 15 times 14 times 13. Holy mama. 2,730. And they both end in 0, so obviously they divide by 10, so it could be 12 out of 273, but then does that simplify?
4 out of 90.
4 out of 91?
Yes.
I'm having an off day. I didn't have breakfast.
You're always on your off day.
I didn't have my Wheaties.
That's why.
Okay, here's where we're actually getting to a tree diagram. So by example 5, I want you to write a tree diagram. We actually have to make this one up on our own, which you're going to have to do on your assignment as well. And once we're done with this, I'm going to have you get out your assignment. We'll do 2 or 3 of these together in class. You do the rest at home. But there was a taste test. 55% were women. 45% were men. So there's the first branch of our tree. If out of the people surveyed, if somebody was chosen at random, what's the chance they were a girl? 55% of them were girls, 45%. So there's the first branch off. So we have female, male. Each branch also has to have the corresponding probability connected to it. So the female, there's 55%. Now 55% isn't a number that you can use in a formula. 55% has to be changed to what? 0.55. And then 0.45 for men. And then each of those have to have 2 branch offs. Because the next sentence here says, of the women surveyed, 75% of them liked the cereal. So that implies how many didn't like it. If 75% did like it, how many didn't like it? 25%. The percentages has to equal 100. So we can call one branch of this likey, and the other branch no likey.
So I choose L and L.
Likey and no likey. What percentage of the women, what percentage likey the cereal?
75.
So that's 0.75. And how many no likey?
The other percentage.
The other percentage, which is 25%.
And then the men is 85, and then the rest is
So 85% of the women like this cereal. So this is the likey branch. And that's 85, so 0.85. And then no likey would be the remaining percentage, which is 0.15. Yep. So now that we have this wonderful tree diagram, we can answer the following questions. If a person is chosen at random, of the people who did this blind taste test, if a person is chosen at random, what's the chance that it was a woman who also liked the cereal? This is an and probability, guys. It has to be a woman, and that woman has to like the cereal. What does the word and mean? Multiply. We have to multiply two separate probabilities. Well, follow the branch of the tree. Okay, follow the branch of the tree. This is a female, and that's a female who likes the cereal. So what do we do with the separate probabilities? You put multiply. Multiply. 0.55 multiplied by 0.75.
Pick the number.
0.55 multiplied by 0.75.
That means 41.45 people.
So 41.25%. There's a 41.25% chance that if a person is chosen at random from these people, you would have chosen a woman who liked the cereal.
Can we just put that in the percentage?
That is 41.25. And then the men would be 0.45 times 0.85.
So the chance that you choose a man who liked the cereal, you'd have to follow that branch and that branch.
Hey.
So it'd be 0.45 multiplied by 0.85.
So it would be
38.25. Now I want you guys to listen carefully and answer this question. How come you have a less of a chance of choosing a man who liked the cereal versus a woman who liked the cereal? Why are those different? There's less men. Yeah, there's less men to choose from. So the chance of, first of all, the chance of choosing a man is less. So it makes sense that it has a smaller probability. A woman who doesn't
So
like.
5 times 0.25.
Yeah, you have to just follow the branches. Let's go. A female who no likey.
It's freezing in here, huh?
Pretty cold.
No, it's not.
Is it colder?
That would be 13.75%.
Oh, that's purple. That's nice.
All right, help me choose a color here. What color?
Yellow.
Yellow?
Green.
Can you guys even see that?
Yes.
Sort of. I can see that.
All right, we're using it. A man who no likey.
0.45.
I eat cereal all the time.
I remember you got cornflakes. I could say something.
0.45 multiplied by
So
0.15.
it's going to be 6.75.
6.75%.
Cannot see that at all. 6.75?
6 point.
Oh, those are Packers colors. You can't have
Ooh,
those.
that's right. Boo.
Get red for the
I hate the Packers.
Whatever.
So, get your worksheet out. Turn to the back. We're going to start at the back. We're going to do a few of these together. Worksheet, turn to the back. We got to make our tree here. So the very first piece of information, the first branch off should be juniors versus seniors. Juniors versus seniors. And remember to add the corresponding probabilities. 60% are juniors, so that's 0.6. So what does that leave for seniors? 0.4. Now of the juniors, sorry, of the seniors right here, of the seniors, 50%. So how are we going to split off, after we split the juniors and seniors, how do we split those up?
Male.
Male, female. So it says of the seniors, 50% are female. So that's 0.5 for female, 0.5 for male. Ooh, 75% of the juniors. What does that leave for the female? 0.25. Nope. Because the only two choices we have are whether it's a junior senior and whether it's a boy or a girl, so we only have to have two branch offs. So one student employee is chosen at random. Take a minute and see if you can do question 5, A, B, C, D. Those are all and probabilities. It has to be both a female and a junior, or a female and a senior. And means what, you guys? Multiply. And means multiply. So just follow the branches and multiply as you go. Give it a try. What do we get for part A? You got 15% over here. What about over here?
15%.
We got a 15.
15%.
Junior, that's 0.25 multiplied by 0.6. I'll take 15%. What about for part B? 20? D is also 20%. A male junior. Now, you guys, before we leave, let's at least set up problem 6. Everybody should have something on their desk writing on. Why do you put stuff away when the bell? Now we got to wait for you to take it out. Bell hasn't rung yet. Let's get it set up. Make sure you set it up right. We work until the end. You don't take a break 5 minutes before the bell rings and stop. Come on. Get it up. We'll wait. Paper on your desk. Paper on your desk. Paper on your desk. Where is it? Where is it? There it is.
My dog already ate it.
Come on. You got to figure out what the branches are going to be. There's 400 fans that are getting food. They're getting either popcorn or hot dogs. 75% of them are adults. The rest are children. So what should our first branch off be?
Adults and children. Actually, you can go 2 ways. You can do adults and children or popcorn.
The first, you guys listen. You have to set this up correctly. Listen. This statement right here tells you exactly how this needs to be set up. It says 80% of the children. So that means we have to have 80% of another branch. So what should that first branch be? Children. And then we can branch out from children. So my question was, what should this first branch be? Children versus adults. That has to be the first branch. We can't make it popcorn and hot dogs because we don't know the correct information. This information right here says 80% of the children. That implies the children has to be one of the first branches. So we have adults and children. Adults and children.
Why do you put adults on top? Adults is 0.75.
75 are adults, so that's 0.75. Children are 0.25. Now we can branch those off onto popcorns and hot dogs.
Oh, I should have given you an age.
Popcorn and hot dogs. So use that thing that I highlighted here. 80% of the children are eating hot dogs. Found in the children branch, 80%.
0.8, and then 0.2 is eating
And then.
Exactly. That means it's going to be 0.8. That means that has to be 0.2.
And then the adults, they'll have, popcorn, 0.4.
This is 0.4 for popcorn. That's 0.6
For
for hot dogs.
So that no one has to do any work.
What's that?
No, see, there's a different problem for everyone.
Where did
You have to answer the question.
and the mint brownies and the creamery ice cream?
They don't sell those bits.
How many did you said obviously should be going to the